AI's next bottleneck is no longer just generating good outputs, it's keeping them coherent, grounded, and fast over long horizons. One NVIDIA paper shows that video models can remember across minutes by retrieving from their own latent history instead of stretching attention until it breaks. At the same time, new work from CompVis and Ultralytics points to a broader shift: unified architectures that turn messy video, multi-view geometry, and real-time detection into one scalable engineering problem. Keep watching, because the interesting part is how these systems trade memory, supervision, and deployment constraints. Let's explore the first paper, Long Live RAG, a general retrieval augmented framework for long video generation. Long Live RAG, developed by NVIDIA researchers with affiliations including USC and MIT, reframes long video generation as retrieval augmented generation over self-generated latents instead of relying only on sliding window attention. The method keeps the base autoregressive video diffusion backbone frozen and adds a lightweight retrieval path, a query embedding from the latest completed latent searches, a historical latent bank. Then the top K-matched context entries are injected back into attention alongside the local window. To make retrieval useful rather than redundant, the paper trains a 1024 dimensional latent retrieval encoder with a reconstruction loss, a window temporal delta loss that suppresses near duplicate short-range matches, and a second-order smoothing term to stabilize the embedding trajectory. Across 3 backbones, causal forcing, self-forcing, and long live, and 30 seconds, 60 seconds, and 120 seconds rollouts, Long Live RAG achieves the best average vbench long rank in every setting, with especially strong gains in subject consistency, background consistency, motion smoothness, and imaging quality. The authors also report that the retrieval overhead is only 4.08 milliseconds per block, or 490 milliseconds total for a 120S rollout, and that K equals 6 is the best retrieval budget under a fixed attention budget. On 30S causal forcing, the full method improves auxiliary VLM exposure quality to 4.7 and beats random retrieval, average pooling, and reconstruction-only embeddings, supporting the claim that content-addressable memory is more effective than fixed anchors or compressed history for long-horizon video fidelity. Let's explore the second paper, Radar Scalable Self-Supervised Novel View Synthesis from Real-World Video. Radar, from CompVis at LMU Munich and the Munich Center for Machine Learning, reframes self-supervised novel view synthesis as a single model scaling problem by collapsing camera estimation, scene reconstruction, and rendering into one feed-forward transformer. The key move is a minimal dynamic state token that absorbs time-varying content during training, allowing the model to learn static scene NVS from unconstrained real-world video without reconstructing dynamics at inference. Training on SpatialVid's 2.7M videos, Radar scales cleanly across 4 model sizes, from 59M to 743M parameters, and the compute optimal frontier is fit extremely well by a single power law with R2 equals 0.997. The final Radar L5762 model reaches 17.11 PSNR on LLFF and 21.38 on the 3 view split, while beating eRazor on the OpenSet benchmark suite with strong zero-shot results across LLFF, DTU, CO3D, Wild RGBD, MIP NERF 360, and tanks and temples. Importantly, replacing Razor's multi-network pipeline with one unified backbone improves both stability and quality, and random order autoregression plus local high-resolution layers raise RE10K PSNR to 29.57 and post-transfer accuracy to 0.92R at 10 degrees and 0.9T at 30 degrees on. Blutrideve Deset. The paper's central claim is that abundant video becomes a scalable supervision source once dynamics are treated as nuisance variation rather than a reconstruction target. Let's explore the third paper, Ultralytics YOLO26 Unified Real-Time End-to-End Vision Models. Ultralytics YOLO26 is a unified real-time vision family built on YOLO1, one that removes distribution focal loss, adds a dual-head NMS-free inference path, and couples training with MuSGD, progressive loss, and small target-aware label assignment to better align optimization with deployment. On CocoVal 2017, the released NSMLX models reach 40.9, 48.6, 53.1, 55, and 57.5 MAP at 1.7, 2.5, 4.7, 6.2, and 11.8 milliseconds on NVIDIA T4 TensorRT FP16, while the end-to-end path stays close at 40.1 to 56.9 millipax. The architecture is lighter than YOLO26 because removing DFL cuts the head from two 6M to two 3M parameters, and from 6.5 to 5.2 G-flops in the YOLO26N example, and the paper reports up to 43% faster CPU inference. Task-specific extensions carry the gains across instance segmentation, pose estimation, and oriented detection, with improvements of up to plus 3.7 mask AP on COCO, plus 7.2 pose AP on COCO keypoints, and mais 3,4 map on data, V-0. The open vocabulary YOLO26 variant extends the same detector to text, visual, and prompt-free inference, reaching 40.6 AP on LVIS minival under text prompting and 38.5 AP under visual prompting, while prompt-free YOLO26X achieves 31.1 AP. That's a wrap on today's AI paper highlights. Thanks for watching.